So thank you very much for the introduction, and thank you again for inviting me to this nice seminar series. And is it working? Oh, yes. Okay. And so I think the idea of combining dynamical system theory and machine learning is really nice and it's really timely. And as far as I'm concerned, I would say that my background is more on dynamical systems theory. So I will not really speak about machine learning because I know very little about it. So just a caveat. And actually, I will not really speak a lot also about dynamical systems theory, but rather I will talk about the intersection and in particular this so-called Koopman operator framework. So basically, my point here is that this Koopman operator, as some of you might already know, is a nice tool that is really in between, at the intersection between dynamical systems theory and machine learning. And so here I consider Koopman operator as a tool to study dynamical systems, a tool to predict them, to control them, or to identify them. And machine learning, or some technique related to machine learning, will help to obtain good approximation of the Koopman operator, because this framework is also amenable to data-driven analysis. And as it had been said already, Koopman operator could also be used in the other way. So it could also be seen as a tool for machine learning to study algorithm, but this will be explained in details in Felix's talk after my talk. And so here the main goal of this talk would be to give you a broad overview, but I will try also to go a bit into the details at some points. But I would like to convince you that first, Koopman operator can be a nice tool to study dynamical systems, but also that machine learning or related techniques can have a crucial role in the use of the Koopman operator. And so during this talk, first I will focus on the Koopman operator, because this is the main tool of interest. And then we'll consider two problems. The first problem is the case of identification, where we'll consider some specific approximation of the operator to identify the systems. So, and in the last part of the talk, I will consider other kind of approximation of the operator based on Reservoir Computer. And so the driving theme during this talk will be the fact that we have to choose specific approximation of the operator depending on the application, the objective that you have in mind. And this is specifically in this context, so to obtain a good approximation, that machine learning related tools can be useful. Okay, so let's start with the Koopman operator. So the Koopman operator, as I said, is a tool to study dynamical systems. So we imagine here that we have a dynamical system, which is described by a flow if we are in a continuous time, but it could also be a discrete, nonlinear discrete map, which describe our dynamical system. So we have an initial condition, and from this flow or from this discrete time map, we can obtain a trajectory. So it's a trajectory-oriented perspective, and in some sense, it is a point-wise perspective because we define our dynamical system for each initial condition, so for each point in the state space. And this is a nonlinear setting because we assume that the dynamical system is general and so it's nonlinear. But here we consider the case of finite dimensions. So we have a finite number of states. So typically the state space is a subset of Rn. And this is the traditional perspective. And there is an operator perspective, which consists in viewing the whole state space at a time. So, and in some sense, we consider a function which is defined on the state space, and we'll see how an operator can act on this function according to the dynamics. So maybe it's not very clear at this point, but I will make things more precise after that. But the idea here is that instead of considering a flow or a discrete time map in a state space, now we'll consider the action of an operator in a functional space, because we are in the space of function f. And the nice thing is that now the operator typically will be linear. So before we were in a nonlinear setting, now it's a linear setting. And what we have lost is the fact that now we have to deal with an infinity of dimension, an infinite number of dimensions. And so it's where somehow the nonlinearity is hidden. And to make some parallel, it's very similar to machine learning techniques where we use a kind of lifting, like in SVD methods, and then we use the kernel trick. It's very similar to hide the nonlinearity behind a larger dimension. Okay, so now let's make things a bit more accurate, more precise. So as long as we consider operators to study dynamical system, there are two operators there that come in mind. The first one is the Perron-Frobenius operator that I denote here with P. And this operator will act on a density. So we consider that we have a density of initial conditions. And from this initial condition, we can consider a trajectory for each one. And so the density can be transported along these different trajectories. So for instance, you have here the red densities, and the quantity of matter in some sense of the density here will be transported to here along the flow, along the trajectory of the system. And so the operator, the Perron-Frobenius, will show us how the density is mapped after some time through the dynamical system. So maybe it's the more conventional way to use operator theory to study dynamical systems. And I would say till maybe the end of the last century, it was the dominant perspective, the dominant framework. So this Perron-Frobenius operator. But there is a dual operator, which is the Koopman operator. And in this case, we'll consider that the operator does not act on densities, but rather on observables. So we'll observe something in the state space, and we'll see how this observation change along the trajectories. And this is also an operator that has been defined a long time ago. So we can trace back to Koopman in 1930. But then it was a bit lost, or maybe more studied in the pure mathematics community. But it has experienced a rebirth in the beginning of the 20th century, especially thanks to the seminal work by Igor Mesic. And in this talk and in my research, I focus on this second operator, so on the Koopman operator. And something I haven't said is that these two operators actually are dual operators. Okay, so now let's make things even more precise. So here, as I said, we consider that the dynamical systems is either described by a discrete time map. So in this case, the time t is a natural number, or it could be a continuous time flow. So t is a real number. But in any case, I describe either the flow or the discrete time map by this function phi. And the Koopman operator is defined very simply. It's the combination between any function, any observable, with the flow phi. So it means that we'll look at the value of f, but along the trajectory of the system. And a way to see this is that if we want to know the value of my new function after some time t at the state x, I should actually consider the value of f at phi t of x, since it's the composition between f and phi t. So I should consider this value, but now this value will be the new value of my new function at x. So in some sense, I will transport this value along the trajectory, but backward in time. While in the case of Perron-Frobenius operator, it was forward in time. Now it is backward in time. So again, we see the duality between the two operators. And something that I haven't mentioned is that now we have to consider the operator in some space of observable. So we need to choose a priori which space of observable we will consider. And in this case, in a very general setting, I consider that this space is given by this calligraphic F. It could be a L2 space, for instance, or the space of continuous function.
So sorry, there's a question in the chat. Enrique, do you want
okay.
to unmute yourself, Enrique?
Yeah. So yeah, can I see the chat?
Yeah, I'm asking him to unmute himself. Do you want to?
I see. But in any case, you can directly interrupt me and ask questions. But I can just read it. So, is it related to the fact that out of an ODE, one can build a transport equation whose solutions are simply transported by the ODE solutions? I'm not sure I understand the question. Can you maybe re-explain the question?
Yes, yes, Alexander. Yeah, I didn't want to interrupt you. So yeah, so normally in the theory of partial differential equations, we do all the way around, right? We say, well, there are PDEs that are elliptic, hyperbolic, parabolic. The hyperbolic first order are transport equations.
Yes.
The velocity field, you know, is giving you the wind that is transporting information, and then people say, well, to solve a transport equation, you simply look to the ODE. The ODE gives you the characteristics, and then the function is simply transported along characteristics, right?
Yes, I think here it's a bit the other way around. Yes, indeed. So we start from the ODE, and which I guess might be related to this notion of characteristic, and then we get a PDE, which is a transport equation. An advection equation. Yeah.
Except that somehow in the thinking of people doing PDE, people will have the tendency to believe that dealing with the ODE, it might be better from at least computationally less expensive and more efficient than working at the PDE level, right?
And in this case, is it still linear then, or then you have to deal with nonlinearity? So
well, the transport equation is linear.
Yes, but
the ordinary differential equation is nonlinear.
Okay,
right?
Okay.
But yet, when one has enough information on the initial data of the transport equation, in the sense that, for instance, when the mass is very localized on given locations, right? People have the tendency to believe that it is easier to transport, you know, the mass according, you know, along the characteristics that one can solve, compute using an ODE numerical solver, rather than solving the PDE, which somehow obliges you to, you know, to establish a grid
sure.
time, and there is plenty of risk of having numerical dispersion and high frequency spurious effects and so on. Well, this is I'm just telling you, right? I'm just telling you how people think when facing partial differential equations and making the link with the nonlinear ODEs associated to characteristics. But of course, it doesn't mean that you cannot go all the way around, right?
Yeah. But thank you for this comment. It's really interesting, and I never thought about this. But I think the main point is that it depends what we want to do. So I can imagine that if we want to simulate things and to have a good numerical approximation, some sort of solution, then it's better to work in finite dimension rather than in infinite dimension. So here, infinite dimension is indeed something that we'll have to deal with, and it will be a limitation from the numerical perspective. So it's a bit my point, the fact that, for instance, machine learning can be useful because we have some limitation because of infinite dimension. But so here, what we want to do is not really doing simulations. At least in my point of view, I'm more interested into theoretical questions. For instance, we would like to study stability, and studying stability of a nonlinear system will be very difficult because you have no systematic methods. I mean global stability. Right. We have no systematic method. We have to find a Lyapunov function, for instance. This is difficult. But studying stability of a linear object, then you just, in some sense, do some spectral analysis and it's done. So it depends on what we want to do, actually.
Well, people normally avoid spectral analysis for precisely transport equations because typically the involved operators are not self-adjoint, right?
Yes. Yeah.
And then they often also lack, I mean, the inverse lacks compactness. So yeah, I mean, a spectral analysis is often very tricky for transport equations, right? So this is why, except when one adds some viscosity on the bundle, in which you get a kind of Fokker-Planck equations for which, you know, you have a better compactness and better spectral theories. The spectral theories are not that much used for transport equations, right? So,
okay.
And also, I think somehow, because transport equations transport everything, so it's very hard to think that there might be some spectral decomposition that reduces the dynamics, right? Because the dynamics of a transport equation is just pure transport. So everything is transported. And then if you give me an arbitrary distribution of mass along, you know, on a given, say, Euclidean space, for instance, then there is no reason why there should be a clear hierarchy on, say, low frequencies versus high frequencies and so on, right?
Okay.
So, but it's true that, I mean, for instance, the work of the, maybe thinking on examples all the way around, one celebrated example is the paper by Diperna and Lyons, where they have shown that because you can build a theory for the transport equation in the infinite dimensional setting, which is simply done in L2, right? As you said, and L2 only needs ordinary differential equations defined almost everywhere. They developed a theory for ordinary differential equations for the Cauchy problem, in which they were not looking to solving the nonlinear ODE for every initial data, but just for almost every initial data, right? Okay. So some kind of generic solvability of the ODE rather than the complete deterministic solvability. Yeah. Okay, but I let you talk, Alexandre.
No, but it's fine. It's interesting, and I've been told that there is no time limit. So
okay. Oh, good. Yeah.
But yes, I completely agree. But here it's not the transport equation; it's the dual, but might be completely related. And also, again, it depends on the setting because, for instance, you were speaking about a spectral expansion. We have spectral expansion depending on the kind of dynamics that we have. But unfortunately, I will not really emphasize this point, but we can have spectral expansion and nice eigenfunction that we can approximate numerically and so on.
Why do you say that it is the dual? Because what I see in your Koopman operator, what you are saying is that the Koopman semigroup is just evaluating F along the trajectory. This looks very much, or is maybe just
no, but it depends. So it was a bit, so I did not expect to do a talk in pure mathematics, so I was a bit less rigorous, but I would say that it's the dual, for instance, if we work in L2. In L2, with respect to the invariant measure on the attractor, then it's directly the dual. Otherwise, it's not directly the dual. And we have Koopman, and then we should consider, for instance, if we're on a Banach space, the dual space, and it's not directly related to Perron-Frobenius, but we can still find connection, but it's not always directly the dual. And but yes, still we can still say this. But speaking of eigenfunction, that will be, for instance, but then I will continue because. But if we consider a dynamics with an attractor, let's say an equilibrium, then we can compute eigenfunction of the Koopman operator. They are really nice. For instance, they are continuous. They can even be analytic. But on the other hand, eigenfunctions of the Perron-Frobenius operator, so the transport equation, will be Dirac function because all the mass will concentrate on the equilibrium. And so there is one approach which seems more suited than another in the case, for instance, of dissipative systems. And it's a bit, my point here is that Koopman operator might be more appropriate in this context. But I completely understand your remark, and I agree with them. Okay, again, please do not hesitate to ask any question, to interrupt me, because I'm not sure I will always see if there are comments on the chat. So I will continue, maybe speed up a bit, because I will try to make things not too long in any case. So as I said, the Koopman operator is a linear operator. So you can directly see that a composition operator will be linear. So we gained a linearity. And, oops, okay. And in the continuous time context, we can define the Koopman operator as a semi-group. So for each time, we'll have an operator. So now it's a semi-group, which will satisfy the group property. And we can define an infinitesimal generator. And again, I'm not enough rigorous, because we need to satisfy some specific properties of the semi-group, like a strong continuity. Otherwise, we cannot define an infinitesimal generator. But when we can define it, which is generally the case, this is defined as a kind of generalization of the derivative. So we have this a differential quotient here, which will define a new operator, which is well defined on some domain. And an interesting thing is that if the dynamical system that we want to study is a solution of an ODE, a nonlinear ODE with a vector field F, then the vector field is directly given, the generator is directly given by the vector field. And we recover this transport equation, advection equation. I'm always a bit confused with the terminology. And which means that if we know the vector field, then somehow we directly know the Koopman operator, and in particular, its generator. Okay, so as we've discussed, so there is just a slide on spectral property. So we can define eigenfunctions and eigenvalues, which will depend on the space that we consider, the space of function we consider. So I denote this eigenfunction phi lambda and the corresponding eigenvalue by lambda, which are then in the spectrum of the operator. And in a discrete setting, it satisfies this eigenvalue equation. And a nice thing is that we can relate these properties of the Koopman operator, these spectral properties, to some geometric global properties of the dynamical system. And another aspect I haven't insisted on it is the fact that the Koopman operator will always provide global properties. So instead of looking at the ODE at a very local, in a local fashion, in the other context with the Koopman operator, we get directly global properties like a global stability, for instance. And so here are a few examples of connection that we can make between eigenfunction of the Koopman operator and some geometric properties of systems, like in the case of limit cycle systems, of equilibria. We can also obtain a global linearization of dynamics and so on. We can also define a Koopman modes, but I will not enter into the detail, which is related to a spectral expansion. And this is also amenable to data analysis. Okay, so the main issue is that we are dealing with an infinite dimensional operator. So it means that as far as numerical methods are concerned, we'll need to approximate the operator in a finite dimension. So to do so, we'll need two things, two ingredients. First, we'll need to select a basis of function, so a set of function psi j of dimension n function, so that it spans a subspace Fn of dimension n. And also, we'll need to consider a projection operator, so that any function in F, any observable, will be mapped to this subspace Fn through this projection. And once we have these two ingredients, we can approximate the operator by a matrix that we'll call a Koopman matrix, and which is defined as follows. So in each column of this matrix, so for instance, the jth column, it will correspond to the projection of the operator applied to the jth basis function. And so in these columns, we'll get the expansion coefficients of this function in our basis of function. So here, this is an important point, because you really see that if we want to have a numerical approximation of the Koopman operator, we need to find to choose a basis of function. And there are an infinity of functions, so we have an infinity of different choices, and there is a choice to make. And this choice will have some impact, some effect on the result that we'll get at the end. Also, this approximation can be obtained from data. So this is related to what we call the Edmd methods. And the idea is that in this case, we select a basis function like monomials, for instance, and the projection operator is a discrete L2 projection. And from the data, it's equivalent to solve a least square problem. So it's very easy, actually. Okay, a last thing is that we can also define a lifted state. So if we consider all our basis function and we evaluate the value of the basis function at some state, then we get a large vector, so a capital N dimensional vector, which can be interpreted as a lifted state. And now the nonlinear dynamics, which were, for instance, in the case of time continuous setting, is expressed as an ODE. Now it becomes a linear dynamics where we have this matrix, either a matrix U or the matrix L, which would be in this case the approximation, the finite dimensional approximation of the generator. So here I put the two frameworks, so either discrete time or continuous time. And so we turn a nonlinear dynamical system into a larger, a higher dimensional, but linear dynamics. And of course, there is an approximation. So this is not exact because this matrix is an approximation since we have this projection which plays a role here. Okay. So I think we are done with the main basic notion on the Koopman operator. So I don't know if you have question, I can take a question now. So please do not hesitate. I can speed up after that also.
Okay. Hello, do you hear me?
Yes.
Yeah, okay. It's Martin Lazar from Dubrovnik. So just a question about your fine dimensional approximation of the Koopman operator. Do you have some a priori estimates on this approximation, some error bounds?
Oh, it's a good question. Actually, there are not a lot of results about this. And it's definitely something we want to do. And I've started to work a bit on this, but there are not so many results because it will really depend on the basis of function that you choose and the kind of operator, especially if it's computed from data. Things can be complicated, but we can definitely use results from approximation theory, for instance. And it's something that we really need to do, especially when we want to apply this machinery to control theory, where these people really want bounds and convergence error and so on. So it's really something we should do at some point, but we do not have so many bounds on the error, to be honest.
Okay, thank you.
Okay, so if there are no other questions, I can go to the second point. So now we can consider the problem of identification. So just an illustration of what we could do with the Koopman operator, and it's one among a lot of other illustrations. And in this case, again, I will try to emphasize a bit the fact that we have to select the basis function in a smart way. So the problem is the following. So when I say identification, I should rather say a parameter estimation. So here we are given a bunch of data points. So we assume that we have pairs of points, xk and yk. And we know that after some sampling time ts, the state xk is mapped to yk. So we get all this pair of data. And from this, we would like to find the dynamical system, so the ODE that generated this pair of data. And in particular, we assume that we know a priori the shape of the vector field. And in particular, we know that it is expanded in some dictionary function that I denote by Gj here. So for instance, it could be a polynomial vector field so that the Gj are monomials. And our goal here would be really to identify this coefficient. And there are different techniques to do so. So the first technique are direct methods. So they compute time derivatives. And once we have the time derivative, we can simply do some regression, smart regression. We can promote sparsity to recover this coefficient CG. But this might be a bit annoying if the sampling time is too small or if it's too noisy. And in some cases, we would like to avoid computing a time derivative. For instance, in the context of system identification from the point of view of control theory, this is something which is forbidden. So we would like to avoid this. And then we can consider indirect methods where we do not use time derivatives, but because the dynamics is nonlinear, it will imply that we have to deal with nonlinear techniques. And typically, this is the topic of nonlinear system identification, where we have black box methods, also parameter estimation. But with the Koopman operator, we have here an opportunity to obtain an indirect method and still have a linear technique. So it's what I will try to illustrate here. So the main idea is to proceed to the following 3 steps. So first, we lift the data. So we evaluate the data points or the states through the basis function. And once we have this, we know that the dynamic will be of this form. So the lifted state, z dot is equal to some matrix, which represents in this case the generator times z. And so here we can simply do some linear identification because we know that we have to identify a linear system. So in some sense, we'll identify an approximation of the generator of the Koopman operator. And once we have this L, we know that the generator is related to the vector field. So we have here again the formula, the equality. And it means that if we know the generator, we know also the vector field. And so we have closed the loop and we have found the dynamical system, the ODE. So this is the main idea. It's also related to some work by Felix, by the way. Maybe we'll also talk about this. Okay, so just to make things a bit more precise, but I will not emphasize too much the details. But so step 1, we lift the data. So we evaluate the basis function in the data points. And basically, we'll construct 2 matrices. The matrices constructed with the value x and the other with the value y. So these 2 values, xk and yk. And once we have this, we can compute a pseudo-inverse here. And this just considering actually a discrete projection on our space, which is spanned by the basis function. And this is the Edmd method. So there is nothing new here. But the new thing is that now we can consider the logarithm. We can compute the logarithm of this matrix. And we can show, we can prove, but I don't give the detail here. We can prove that the logarithm of this matrix will give us an approximation of the generator of the Koopman operator. And then last step, what I call the lifting back, we can consider some specific basis function, which are the identity function, I call IDJ, which means that we just select the jth component of the state. And it's easy to see that if we apply the generator to this basis function, that will get directly the jth component of the vector field. And in the context of the approximation, we'll actually get the projection of the jth component of the vector field. And in particular, in the corresponding column, we'll get all the coefficient, the expansion coefficient in the basis of function, which means that we'll get directly these coefficient CI. But there is a condition. First, we need to have this identity function in the basis function, but we also need to have in our basis function the library function. So this function GJ should be in the basis function. So we need to select once more the basis function in a smart way. And so we have this theorem the fact that if we have chosen properly the set of basis function, then we can prove that if the sampling time tends to 0, then the error on the coefficient tends to 0. So we have no, again, no bound on the error, but at least we have a convergence, a guarantee. And you could say that the idea was to obtain a method such that it works with a large sampling time, but still we need a sampling time which tends to 0. This is true if we want a 0 error, but still with a kind of large sampling time, not too large, but not too small either, we can obtain good results. So for instance, here, you can see that with a 0.5, in the case of the van der Pol dynamics, we can still obtain a very small E error. And what could also think, what happens if we do not choose properly the basis function? So if we do not choose the function Gj in our basis function. So if we do not pick the library function. In this case, we do not have conversion of to 0 of the coefficient, Ci, but we can see that we can show that the approximation of the vector field will tend to 0 in L2 error. And we need, in this case, a condition. So there are a few technical conditions, but I have not written everything here. So I will refer you to the paper if you are interested. But the main condition is that the set of basis functions should be dense in our space of functions, so in L2 norm. And in this case, you have a convergence of the vector field, the estimated vector field, to the true vector field in N2 norm, if the sampling time tends to 0, but also if the number of basis functions and the number of data points tend to infinity. Okay. So again, this illustrates the fact that basis function should be chosen in a smart way, in a good way. And probably that machine learning could be helpful in this context. Here are a few examples. I will not discuss a lot about this, but just to show that it works. We get very accurately the exact value which are in blue and approximated, the estimated value of the red crosses. We have also compared this method with just estimating derivatives with a central difference method, and we see that the results are much accurate with this lift-in method based on the Koopman operator. We can also apply this to PDEs. So we could do the same to identify nonlinear PDEs. In this case, we need to define the Koopman operator on PDEs, because when we use a Koopman operator, we start from a finite dimensional system, and then the bad thing is that we end up with an infinite dimensional object. But in the case of PDEs, in any case, it's already in infinite dimension. So why not extending even more the dimension? Since it's already infinite, it will be somehow a bigger infinity, but still it's an infinite dimension. And so we can define the Koopman operator for PDEs, and we can use the same trick. So if you are interested, there is a paper. And again, it gives good results. Not as good, I would say, as for ODEs, but it's still a preliminary result, but we can identify nonlinear PDEs in this case. So it's just a parenthesis. Now we could just forget the case of PDEs and come back to the identification of ODEs, of nonlinear ODEs. And there is a main issue. As I said, we need to include all the dictionary function in our basis function. But imagine that we have a very large system, high dimensional systems. For instance, if we want to identify a network, and imagine that we know that the vector field is polynomial, then we have a lot of monomials to consider, and it really blow up in a combinatorial way. And so this is really an issue, because we have too many basis functions to consider. And with this method, because we consider a least square regression, a least square optimization, we need more data points than a basis function. And so we can circumvent this issue by considering a kind of dual method, which is a bit related to a kernel-based method in machine learning. So the idea is that instead of considering these matrix where we have the pseudo-inverse of x times psi y, we'll consider psi y times the pseudo-inverse of x. And now this gives us a matrix k by k, where k is the number of the data points, while in the previous case, in the main method, we have a matrix n by n, so the number of basis functions. And if we look at this new matrix that I call U-dual, actually could be seen as a kind of change of variable. So we can still make the initial matrix U appear, but it is in between two other matrices, which acts like a change of variable. And this change of variable, so this change of coordinates correspond to going from a space of observable to a sample space, where in some sense we'll represent any function through its value at the sampling point. From a functional analysis point of view, actually what we do is to consider the dual operator, which acts on a subspace of evaluation functionals. So we can again do the same kind of proof as before, also obtain convergence result by considering that we are in a dual space. And to make also connection with machine learning, we could interpret these matrices psi y and psi x as a kernel matrices. They take into account inner products between evaluation functionals. Okay, so again, we can now use the same method. So I will go fast using these three steps. And what we get in the end will be the value of the vector field at the different sample points, at the different data points. So now that we have the value of the vector field at the different data points, we can use some regression, use promoting sparsity using the lasso method, or even any kind of machine learning that you would like to then obtain the coefficient Ci which correspond to the expansion in the library functions. Again, we have convergence result, but I will not discuss this. And just an illustration, and then we'll have finished this second part. We could consider that we have a network of 100 nodes, for instance, and we have a dynamics which is attached on each node, which is in this case the polynomial dynamics. And we'll consider that we have a link between one node to the others if the dynamics of one node is influenced by the dynamic of the other nodes. So it's a bit inspired from what we would have in genetics, where we want to see which gene influences as effect on other genes. And in this case, so if we have 100 nodes, 100 states, but we consider a few monomials up to degree 3, then we have almost 200,000 coefficient to select for each dynamics, for each state dynamics. And still, yet we consider only 1,000 data points. So much less data points than the number of coefficients. But there are a lot of zero coefficients. And so we can apply these dual methods, obtain the values of the vector field at the data points, and then do some sparse regression to obtain the coefficient. And this is what we get. So we could think that it's not so good, but actually if we zoom in, we see that we have a very few false positive actually. So when there is really a value, sorry, when we estimate that there is a non-zero value, then there is indeed a non-zero coefficient. And since we are in the context of network identification, so we can consider correctly identified links and incorrectly identified links, and we see that there is only 4 incorrectly identified links. So a very small number of false positives. And for those who are familiar with, here is the ROC curve, and we see that it's quite good. but of course, these are synthetic data. Okay, so this concludes the second part. Yes, there is a question by Robert.
Hi, yeah, thanks. Yeah, I have a question about your step you're calling lifting back.
Yes.
In general, a linear operator doesn't necessarily come from a vector field. For example, if we just take a quantum evolution, then it comes from, you could call it coming from a non-commutative vector field, but it doesn't come from a vector field.
Yes.
So what steps do you have to take to be sure that you get a vector field?
Okay, so it's a good question. And first of all, I have often a question about lifting back, so I should not call this lifting back. Maybe it's not well chosen. But in this case, I really assume that L is the finite dimensional approximation of this generator, which comes from a vector field. So if I do not have a vector field, I should actually not consider this method because it assumes that there is a vector field. But in any case, it will give me a result, but probably not a good one, because since I assume that this is the approximation of the vector field inner product to the gradient, then I know that if I consider the identity function, that I will get the corresponding component of the vector field. So if it's something else, maybe we should consider what is the generator in this case, and then we can expect what we would get as a result. But my main answer is that we should not consider this setting as it is if it's not, if the data are not generated by the vector field.
Okay, thanks.
Okay. So how many minutes can I still consider to finish the talk?
Yeah, as I told you, feel free to just expand. I mean, because initially I was assuming that Felix would start at 2:30. So yeah, so it's up to you.
Okay, so it will be finished before, I think.
Yeah, all right.
Maybe 15 minutes should be fine.
Yeah, that's all right. Yeah, thank you. Yeah.
So now the work the first work I presented was a joint work with George Consalves, and now this work I will present is a joint work with my PhD student Marvin Gulina, so at University of Namur. So it's still an ongoing PhD, so it's also an ongoing work. And the very basic idea and the motivating idea is that we forget the idea of identification. For instance, if we think of a network, it might be very difficult to identify a whole network if it's very large, because simply we do not have measurement at all the nodes of the network. And so we forget this idea, but rather we'll focus on other objective. And in particular, in this case, we want to extract some spectral properties from the dynamics through the spectral properties of the dynamical system. And some motivating application, but that we have not developed yet, but are the following one. So for instance, we can show that we can proceed to some spectral network identification. So if you only have a few measurements at a few nodes in a very large network, you can still obtain the spectrum of the Koopman operator, or at least an approximation of it. And if you get the spectrum of the Koopman operator, there are some analytical results that show that it's related to the spectrum of the underlying network, so the spectrum of the Laplacian matrix of the network, which can tell you something about the topology of the network. So you have only local measurements, but still you can get global properties of the network, for instance, like the mean degree of the nodes or the maximal degree of the node and so on. And so this is one motivation to get a spectrum of the Koopman operator from data. There are other works, for instance, by Amit Surana, which shows that we can use the spectrum from the data to do some time series classification. We could also think of event detection. So when we detect some change in the spectrum of the Koopman operator, we detect a change in the dynamics. So again, there are interesting connection, I think, to machine learning, but in this case, more as a post-processing step. And so here the idea is to obtain a a good, and I would say the best finite dimensional approximation of the operator, such that we can expect that the spectral properties that we have computed are accurate. And just to make things more clear, in the case of the Edmd method, so the classical method, what we do is that we predefine the set of basis functions. So we choose it, for instance, monomials of a Gaussian radial basis function. And what we'll do is doing an optimization on the value of the matrix U. So it's a least square regression where we'll find the best linear combination, so in the components of U, such that we minimize the square error. And another way to do this would be to think of also learning the set of basis function. So not only we'll try to find the best Koopman matrix U, but also we'll try to find the best basis function psi. So we optimize not only on U, but also on psi. But psi are typically in an infinite dimensional space because these are functions. So this problem like this is intractable. But then there is a smart idea, again by Felix, that propose, Felix and colleagues, that propose to use neural networks to find the best basis function. So the basis function will be, how to say, will be equivalent in this case to a neural network. And so they propose a solution. And here what we do is nothing, not much more, I would say, just using, instead of using a neural network, we'll use a specific one, which is a reservoir computer. Maybe with the idea that if we have a neural network, it might involve nonlinear optimization. And with a reservoir computer, we only have to consider linear optimization, so least square optimization. And so just as a reminder, but I'm sure that most of you know much more than me about reservoir computers, because I'm not an expert. So the reservoir computer is made of a recurrent neural network, so with N0 internal states on each node of the network. And the dynamics on this network is given here by this discrete time dynamics. And here we have some weights between all the nodes of the neural network, which are chosen arbitrarily between -1 and +1. Also, this network is forced by some inputs, which in our case will correspond to the state of the dynamical system. And again, with some weights, W in, which are chosen arbitrarily. And after that, we can obtain outputs. And these outputs will be typically our basis function and are obtained as a linear combination of the internal state and possibly also of the inputs. And the coefficient of this linear combination are the W out, and these are the values that are trained during the training. So this is the reservoir computer. And so we have used it in two different ways. First, a very naive way. We just tried to see if we could use the internal state of the reservoir computer as a basis function, directly as basis function. So it was really naive because we did not think it would work because there is no training in this case, but still it could yield a good result, at least a result of the same efficiency as the classical Edmd method. And one reason is that because it's a recurrent network, we consider delays, and sometimes considering delays is good, actually, in particular if we cannot measure all the state of the system. So we have a kind of delay embedding in this case. Okay, and the second method is the fact that we consider the output as basis function. So in this case, so we know that the output will be a linear combination W out times the internal state, time S, so which appears here, Wi time S, and here Wi time S. So this is the function the basis function psi, and we optimize not only on U, but also on W. And to solve this problem, what we do is an alternating scheme, where in each step we fix one matrix and we optimize on the other. So I think in Felix's work there was always already an alternating scheme, but now the difference here is that we only have to proceed to a linear optimization in each of both steps. And so, okay, I think I've said almost everything. So yes, maybe something that I should add is that still this is a nonlinear optimization problem, but because we have divided in these two alternating scheme, then it becomes linear, but in the end, this problem is still nonlinear actually. So there is some nonlinearity which is hidden behind. And so just to finish with a few results. So first, we've considered some reconstruction properties and also prediction properties, even though it was not the main goal, but still it yielded a good result, not exceptional, I should say, but it yielded good results. So the idea here is that once we have the basis function, which are given by the outputs of the computer, the reservoir computer, then we can get this Koopman matrix. And this Koopman matrix, we can iterate it, apply to some initial condition, and iterate the matrix. And yes, I should have put S instead of X in this case. And so it means that we mimic a nonlinear system, but through a linear system, a high-dimensional linear system. And we can see that, for instance, in the case of the Mackey-Glass system, we can reconstruct more or less the data. We can capture the oscillation and the transient of the data, but still with a linear system. And we can also consider another initial condition, and we can predict the system, the future trajectory of the system, but again with a linear system. So the main goal here was not to do prediction, because if we want to do prediction, probably that a nonlinear method would work better, because we want to predict nonlinear dynamics. But still, we can end up with some satisfactory results, even with a linear Koopman dynamics. And finally, we have computed spectral properties, and this is still an ongoing work that we will also apply this result to some specific application like identification or classification, as I said. And we have done this for the Duffing system and again the Rössler system. And for instance, in the case of the Duffing system, we can see that with the second method, we capture the Jacobian, the eigenvalue of the Jacobian matrix along the computed near the equilibrium. And we know that this eigenvalue should be in the spectrum of the Koopman operator. In the case of the Rössler system, we can see that the Edmd method will produce unstable eigenvalue. So this should be a spurious eigenvalue because we expect only stable eigenvalues, while the method 2 and 1 also only produce a stable eigenvalue. But the difficulty here is that Rössler system is chaotic, so it's not clear what is the spectrum in this case, and especially the spectrum will depend on the space of function that we consider, and it's not clear which space of function is considered since we've used this reservoir computer. So it's not obvious to know from a very rigorous and analytical point of view what is the functional space that we consider, and so what should be the spectrum in the end. But we'll try to validate this through application and see if it can yield better classification results. For instance, if we use this reservoir computer instead of the classical Edmd method. So I think this brings us up to the end of the talk. So just to summarize, we've considered another perspective to study dynamical systems, which is based on the Koopman operator. So now we work with a linear operator, but in infinite dimensional settings. And I have tried to illustrate this in the context of identification and also in the context of trying to capturing the spectral properties of a dynamical system through a computer reservoir. And the crucial point is that we need to select a finite dimensional approximation of the operator, and it means that we need to choose a set of basis functions. And so this is a very important point, and a crucial role of machine learning could be, and it's already the case, can be useful to consider to select this basis function in a very smart and efficient way. And so I hope that I have convinced you that this Koopman operator is one tool among others that is a bit in between machine learning and dynamical systems theory. And it can be helpful to study dynamical systems from a global perspective, but it needs also machine learning as long as a data-driven context is considered. And I hope you are convinced that it's a nice framework for the interplay between dynamical system theory and machine learning. So I thank you for your attention.
All right, thank you very much. Any questions?
Just clarification. Early on, you mentioned black box method. Very quickly, just in passing, you mentioned it.
Yes.
Is it in the sense of machine learning or deep learning?
I don't think so, because I'm not very familiar with classic input-output system identification in the context of control theory, but I mentioned methods that date from maybe a few decades, so not deep learning. No, I don't think I was mentioning this, but there might be some connection. But
So
I mean black box
maybe,
in the sense that it's hard to also interpret, so that there is no model base of physical properties, physical meaning.
right. So there is a big issue still in machine learning and in deep learning about explainability.
Yeah.
So could be that what you found about the Koopman may help there because you are connecting to machine learning.
Please go ahead.
This could be a very interesting direction if you can, on the basis of the theory of Koopman and what you demonstrated, could be used for explainability of these methods in machine learning.
Yeah, I have already heard this kind of suggestion. I think indeed it's very relevant. But in my case, I'm more using machine learning to study dynamical systems, and maybe Felix in the next talk will be more in this focus. So trying to explain algorithm in machine learning and maybe deep learning. But there are some recent results where, for instance, the optimization that is performed to train neural networks is seen as a dynamical systems, and then is studied through the Koopman operator. So this is a direction that some researchers have already taken, and indeed it's very relevant.
Okay, thank you. And maybe quickly, another curiosity. At the very beginning of your talk, the first part,
yes,
I asked myself, is there any, when you talk trajectories and initial values, I asked myself, is there any connection here to ergodicity?
Yes, especially the Koopman operator was maybe not by Koopman, but also Van Neumann. You consider the Koopman operator almost at the same time in 1930-32. And it was in the context of ergodicity. So for ergodic systems, we would, for instance, work on L2 space with an invariant measure. And in this case, we know that the operator is unitary. So it's why we use usually the capital U to denote the operator, because it was in this context unitary. And then, for instance, we have a nice spectral expansion and so on. So there is a very strong connection to ergodicity and ergodic theory in general.
Okay, thanks.
Hi, I have a question.
Yes.
So earlier on in the talk, the first part about identification, you had a slide with some examples. One of them was the chaotic Lorenz system.
Yes.
When you look at the coefficients, you have crosses for the correct ones. There are a couple of them. Yeah, that's the one. So, sorry, circles for the exact ones. They look to be sort of overlapping with 0, and the ones that are sort of you're not meant to look at, they're not needed to reproduce the equation. If you understand what I mean.
No, I don't understand.
Sorry. So there's a long row of red crosses. Yes, and then you've got 4 blue circles that pretty much overlap with the red crosses. Yeah. So how did you know that those were good coefficients compared to the other ones that were 0?
Oh, okay. So actually, I put with blue circle non-zero coefficient. So maybe it's a very small value, but not a 0 one. So, and so I did not put all the 0 value, but I know the true answer because these are just simulated data.
Sure. So the estimated ones, are you saying that they were kind of machine precision level 0 just from your method, or were you setting them to 0 during your method?
Okay. So it's no. Okay, I just put directly the value I got. So I consider this this jth column, and I just put all the coefficients. So probably it was 0 or very, very small. I don't remember, but.
Okay, so you didn't use any extra sort of sparsity type thing, or
no, not threshold. In this case, no. But with the dual method,
yeah.
Then I did because I used the lasso method, so I have to tune this lambda parameter.
Okay, great, thank you.
You're welcome.
All right. Any other questions?
I have a question. Hello.
Yes.
Hello.
Hello. Thanks for the very nice talk. I had a first question about system identification. So I understand from what you said that for predictions, a nonlinear method would be more efficient, more accurate than predictions with the Koopman operator. And my question was then about system identification itself. Then what would be the advantage of the Koopman operator methods as compared to, for example, the direct nonlinear methods, such as interpolation, to have an approximation of the vector fields? Like you sample, yeah. So I don't know if my question is clear.
Yes, I think so. So you mean, for instance, compared to these linear techniques and direct?
Yeah, but for example, if you sample the value of the vector field on some sample points and then just do an interpolation, with how does that compare to the EDMD method, for example?
When you say the EDMD method, you mean the method I proposed?
Yes.
Okay.
Sorry, yeah.
So it's a bit what I did, but I should admit that I did not make a very extensive comparison between all the different settings. But if you have a sampling time which is too high, then this will not be very good because your estimation of time derivative will be very bad. And then you will get bad results. So it's a bit what I did here. So here I just compared actually, so I computed the coefficient, then I reconstructed the vector field. And of course, I use a very naive method, which is just central difference. So you compute the vector field by central difference, and you see that if the sampling time is too high, then the error is much larger than with the lifting method, which stays very close to 0 for a longer time.
But by lifting methods, you mean taking the logarithm, right?
Yes, the method.
Oh, okay.
And what is the other method that you mentioned then?
No, okay, I was just imagining that, for example, if you're able to sample the value of the vector field in some sample points, then you can do an interpolation, for example.
Yes.
From what you say, sampling the values of the vector fields would imply doing like finite differences from observations of the trajectories, right?
Yes, because you only have trajectories and you need to but because you do not have the vector field, you just have points on the trajectory. So the only thing you can do is to estimate this derivative to get the vector field. And so here I use central difference. Maybe we can use some smarter trick. And in some sense, the lifting method is a smart way to compute the time derivative field. But okay. In an indirect, so it's a better approximation because it takes into account that it has this exponential form. And central difference, it's computing the exponential at the first order. And here I consider to a larger order.
Okay, yeah, thank you. It's much clearer now. Thanks.
Thank you.
All right. So if there are no other questions, let's thank the speaker. Thank you very much.
Thank you.
Yeah, thank you.
So I have to, is it fine? I think my screen is not shared anymore.
Yes, yeah, I think Felix maybe.
Yes. Do you see it now?
Yes, we see it, yeah.
Now you see the full screen, right?
Yes.
Okay. Yeah, thanks also from my side for the invitation. And also thank you, Alex, for the great introduction to the Koopman operator. Now I don't really need my slides anymore. Maybe I can skip over them a little bit. Because as you said before, I'm not really gonna talk about sort of the main ideas behind the Koopman operator. I'm gonna talk more about how we can actually use it in terms of applied mathematics to study algorithms. So a sort of a specific subset of dynamical systems, if you want. This is a joint work with a PhD student from Yannis Thomas at Princeton, and of course also Yannis Kefrikidis, formerly at Princeton, now JTU, and that we did, I think, 3 years ago, and that apparently has gained some interest, which is very nice. I also liked really much the questions from before, and I think this quotation that I usually always put on the Koopman operator talks fits quite well, because as a mathematician, we might think these things are very beautiful, but of course there's also other people who don't really care about theory all that much and that want to just understand dynamical systems in any way they can. And so I think the Koopman operator theory framework fits perfectly for this quote, even though of course it's about LaTeX and not Koopman, because the ideal situation occurs when the things that we regard as beautiful, so in this case Koopman operator theory, are also regarded by other people as useful. And I hope I can give you some idea of what is useful about this theory. I will quickly talk about the motivation why we want to study algorithms in particular as dynamical systems. Then I guess I can briefly go over my take on the Koopman operator theory, but you have heard about the Koopman operator approximations a lot in Alex's talk. And then I want to go deeper into qualitative and quantitative analysis of algorithms. So I will talk about convergence, uncertainty, high dimensional problems, generators, especially because you've also heard about them before. Then something we I think haven't discussed in Alex's talk, which is chaotic behavior, in this case also of algorithms. So why do we want to study algorithms in general? Well, we certainly want to understand which algorithms are stable or unstable, right? Because using unstable algorithms for any problem is usually a bad idea. So we want to certainly sort these out and understand at least in what part of the domain algorithms can be stable, where we can use them. And a bit more refined is the second question. So which algorithms are actually similar and different? And here I specifically want to talk about similarity, not so much in the quantitative sense, right? If you think about neural network approximations, then you might think, okay, this network is this accurate and this network is this accurate and so on. This would be more the quantitative sense, like which algorithm is quantitatively better. But what I'm going to talk about is more which algorithms are qualitatively different. And what I mean by this in a very quick example is that one algorithm might have one global minimum that it approaches, while another algorithm might have 2 or 4 minima, and they would be qualitatively different. But of course, a stable and an unstable algorithm globally would also be qualitatively different, even though a qualitatively similar algorithm might have different quantitative behavior, but also just one minimum, for example. And the third question, I guess, nowadays is even more relevant than it was 30, 40 years ago, because now the algorithms that we have are usually implemented in very large software frameworks that we cannot really dig into because they're maybe hidden in some company code, proprietary codes and so on. So we kind of, in most cases, would have to study algorithms numerically. And well, I would say even in the easier cases, it's also very difficult to really gain an understanding of an algorithm in an analytical way, right? Most algorithms, I would say, do not really have closed form solutions, especially because if they had, then we wouldn't need the algorithm. So the third question is, can we study them numerically? And of course, our take on it is that yes, and we can use the Koopman operator approximations to do that. So the line of argumentation for the work is that we certainly can study the Koopman operators for dynamical systems, and you've seen Alex talk about it at length. But now the key idea here is that algorithms, especially iterative algorithms, right, are or can be considered as dynamical systems, because if you think about it, if you have some state xn and then you just apply an algorithm, then you get the next state over time. And in an immediate example would be a solution algorithm to an ODE, which of course is directly tied to the dynamical systems context, right? You have some dynamical system as an equation, differential equation, and you apply a numerical integrator algorithm to the state to get an approximation of the next state in time. But of course, this also applies to algorithms that are not embedded in the dynamical systems theory context. Think about optimization algorithms and so on that also have an iterative component. But of course, since 1 and 2 hold, we can do 3. So we can study Koopman operators of algorithms in particular. Which algorithms did we actually study? Here are 3, or if you take a closer look, there are actually 6 different algorithms, because I always put the continuous and the discrete version on the slide, mostly because I wanted to make clear that the typically discrete type algorithms that we use in practice have continuous analogs as well, even though obviously the solution to these equations do not usually exactly pass through these points, right? These are sort of approximations to these if you want, but you can also go the other way and say, okay, these are the continuous version of some algorithm that we use. And here I show the gradient descent method, which I guess is mostly used nowadays for neural network training, Newton method, and the corresponding continuous version, the Davydenko method, and then Nesterov, which is also used for neural networks. I guess what is not, right? Nesterov method, which has the specific additional property above the gradient descent method that it can oscillate around the target and overcome small minima. And so one motivating example with the Koopman operator, and if you've never seen anything beyond Alex's talk, of course, then this might be interesting. So let's take the Himmelblau function here, which is just a real valued function in 2 variables. It has 4 global minima, so all these values are the same, and it has several saddle points in between. And we can, of course, start anywhere on the plane and just minimize this function, or try to minimize it using gradient descent, right? And then we will hopefully reach one of these minima. And what we did, just as one first example that I will go into later, is we sampled points on the plane, so in the x1, x2 coordinates. These are the blue points, and then we applied 1 step of gradient descent, so with a very small step size. And you can almost, maybe you can see it, that there some of the points kind of go towards these global minima a little bit. And already with this data and the radial basis function dictionary that you should now understand what it is, we can use this data to approximate the operator, and then also, for example, use it to move forward in time, right? Like we don't really interpolate any vector field here or anything. We just use the operator, compute its eigenfunctions, and then propagate forward in time, and we get very similar, like indistinguishable trajectories that all reach the global minima that they would reach if you would just apply gradient descent as well. I mean, you've seen the motivating examples. This is sort of the first example, I guess, from IGA for the Koopman operator, but maybe I can skip this now because even Alex showed this picture. I can also briefly only go over this, my take on why the Koopman operator in general is interesting. Integration is trivial once we have it, right? So because once we have this linear map and it's a good approximation, we can easily integrate a dynamical system or the behavior of an algorithm. It is a global linearization, even though, of course, in the machine learning context, one has to be careful with these global statements, because global in a machine learning or data-driven context always means where we have data, right? It's not like on the whole plane, it's just inside the little box. But it certainly is more global than just a local linearization that is usually being done for these systems. The third point is also interesting because we can estimate it from scattered data, like from this data I just showed on the slide, where we have some initial points and some points right after. And this fourth point is kind of pulled under the rug a little bit in most papers nowadays, because the operator has almost all information about the system. But if you look in the chat, I put one nice paper about the discussion of Ullmann and von Neumann about this small almost word here, because for some systems that are chaotic and have a mixed spectrum, the operator actually does not have all the information. But for all practical purposes, it really does. And it still makes sense to approximate it numerically. This is the defining equation, right? You have some observable in some space. You apply the Koopman operator, you get another observable. And this observable evaluated at some point, or some algorithm state X, is the original observable evaluated in the future, so after this algorithm step. And this kind of tightly explains why the Koopman operator is tied to the dynamics of the system, right? Because it has this property. And linearity we've already seen as well, so I don't really need to spend too much time on it. But I guess the crucial point is that it doesn't act linearly on the states, of course, right? It acts linearly on the observables, on the functions of the states. And it also goes back to the dynamics of states, but Alex has shown a very nice picture and I don't have it, so I don't really want to bore you again with these details. What we haven't seen so much, at least before, is that, of course, we can decompose it into eigenfunctions. But then what we can also do in many systems is that the eigenfunctions actually also form a basis for the space of observables, or at least they form a basis for observables that we care about, right? So that would mean that if we care about some observable G, let's say the temperature of a system, or I don't know, the behavior of some algorithm over time or over iteration number, then we can decompose this interesting observable into the eigenfunctions of the Koopman operator and just use it to propagate in time, instead of simulating the system in a very complicated way. Mostly because if you think about large black box algorithms that take millions of lines of code and maybe a supercomputer to actually even run, then computing eigenfunctions and propagating the interesting observables in this way certainly is easier than running the black box, right? But always, of course, under the assumption that we have access to some form of data from this complicated algorithm already. So this kind of brings us back to the earlier question of that to actually gather data on this operator, we also need to run the original system, right? So sometimes there's a real trade-off, and sometimes the trade-off is not really there in terms of using this as a surrogate model. But I would argue that it is still useful to compute the operator. In this case, also related to an earlier question about interpretability, and I will go, or explainability, sorry, and I will go into this in more detail in one of the examples. But let's go back to the algorithm case now. I have a very small example to illustrate the main point here. So let's say we have a differential equation like this, just a very simple linear differential equation in one dimension with this parameter alpha here. And I guess most of you just immediately know the solution, of course. And let's assume we don't know the solution and want to solve it with Euler's algorithm. So just this one here. This would mean replacing the vector field f with minus ax, right? And so we have this as the next state in time. Then certainly system 3, so, well, it's the numbers are missing, no. System 3 is different than system 2 with different behavior, even though system 3 kind of tries to approximate the behavior of system 1 or system 2. And if you now want to use the Koopman operator to explain this difference in behavior, in this case, even qualitative behavior, then what we can do is very straightforward, right? For example, we can pick the space L2 on the subset of Euclidean space that contains functions that map to the complex plane, and just use the standard definition of it, where now the action of the flow of this algorithm here is defined pretty much exactly like this, right? It's very simple in this case. And if we now go one step further and consider only the monomials in the L2 space here and see what the Koopman operator does to them, then we can immediately see, okay, for the continuous time system, this is the solution, right? If without Euler's algorithm, and that means pulling in the k exponent from the monomial, you can see that this is an eigenvalue and this is an eigenfunction, right? Because we started with some monomial, we get the monomial back and just multiplied with a number. So the monomials in this case are eigenfunctions of the Koopman operator for the continuous system. But now, interestingly, for Euler's method, right, we can also use the monomials, of course, because we act on the same function space. But Euler's method has this flow map, which means these are the eigenvalues. So crucially, eigenfunctions of the Koopman operator for Euler's method are the same as the ones for the original system, but the eigenvalues are the same. So the spectrum is different. Of course, if you've ever done numerical analysis, maybe, then you also know that Euler's method still converges, and this is still true in the spectral sense, of course. But I think it's a good example to illustrate that we can analyze algorithms in this Koopman operator framework and also obtain useful quantities even without doing any numerical computations, right? Like we can show a spectral convergence, in this case of a very simple method to a very simple system, but still. Let me take one step back and now give a brief overview of the numerical algorithms. I also have to, I can go through them a little bit quicker because you've seen some of them already. The original one, a dynamic mode decomposition, so no EDMD by Peter Schmidt, mostly considered the linear PDE case, not the linear Koopman PDE, right, but just regular linear PDE that people try to understand. And he developed dynamic mode decomposition for these PDEs without any reference to the Koopman operator. This was discovered by Igor Mesic later. Then Laplace averaging, for example, uses a Laplace transform to approximate eigenfunctions for sort of single trajectories. EDMD or kernel DMD, which Alex also talked about a little bit, uses scattered data. So this pointwise data that has the current state and the one state in the future scattered all over the place in the state space. This is for EDMD, and yeah, and many more. It seems that everybody who works with the Koopman operator kind of has to invent their own numerical technique, and of course we did as well, as you've seen before. And there's other sparse coding techniques as well. And of course I should have put Alex's method here as well with the lifting. But the EDMD idea I explain a little bit more on the next two slides again, mostly because we used it for all the following results to study these algorithms. So essentially just define a function space by picking a basis. And of course, this is the very crucial step, as Alex has said, because picking the basis poorly will result in a poor approximation. If you have snapshot data like this, you can just evaluate this basis on it and then approximate the linear map. This is how we wrote it in the paper, except for this little one mistake. So if you take a look at the algorithm in our paper, at least, please take a look at this and think about a correction. So this is the correct one in the paper. I think it's A transpose A, which is wrong. But the general idea is that, yeah, as I said, you pick a dictionary, monomials, radial basis functions, neural networks, whatever. Then you evaluate the Koopman operator on this dictionary pretty much by just picking the next point in time and evaluating it there. Then you have this matrix A. And then in this case, you just do least squares to actually get the approximation of this Koopman operator matrix in the basis that you chose here, right? And of course, if you choose more basis functions, usually the approximation gets better, should get better at least. And if you choose a poor basis in whatever sense that is, then the approximation is also poor. But let me now go over a couple of examples, right? This first one is more the standard way to use the Koopman operator if you do not want to delve into spectral theory and analysis and so on, and if you literally just want a surrogate model for your algorithm. So this is the Himmelblau function again. I already said that we can approximate the operator using this data and in the radial basis function basis. So essentially on some of these points, you put little bumps, right, and use these bumps as our dictionary. Do the steps I just showed you, the EDMD step, and then we have an approximation of that matrix, and then can use it for prediction. But now the next step here, this one is, I think, something that I should talk about a little bit more because of the question earlier with explainability, right? Because we can immediately use the results we get here and with the spectral decomposition into eigenvalues and eigenfunctions to also explain what the operator, what the method did. And I think this would be extremely difficult, or I guess impossible, with just a regular interpolation and doing the vector field, for example, for this. Or if you want a trained neural network to predict the states, you would not get a picture like this. And what is shown here is an ergodic decomposition of the state space using the first four eigenfunctions of the Koopman operator that are associated to an eigenvalue 1 in this case, or 0 if you take the infinitesimal generator, right? So, and what it means to have an eigenfunction at eigenvalue 1, I guess is clear from the formula, right? Like if you apply k to the function is equal to 1 times the function, so you get the function back. But what happens if you numerically compute the operator, you get 4 of these eigenfunctions, or even more in some cases, and they explicitly separate the basins of attraction in this system, right? You can see that they cut through this here, and they actually sort of converge in the cell point here. And what I'm not showing here is that, for example, let's take the function that is green on the top right here. This function has some non-zero value up here and is 0 everywhere else. And so here I just sum them up. They take on different values in the basins of attraction. And you can, from the spectral theory, and of course understanding what it means to have an eigenvalue 1, you can immediately explain what will happen. And you can also use it to directly count the number of steady states, for example, of your algorithm, right? Even though you might not even be able to look at this picture if your underlying state space is 100-dimensional. But if you see that your approximation yields 4 eigenvalues equal to 1, then you know that there's 4 different bosons of attraction. Always, of course, modulo the numerical approximation difficulties. The next point I will go over quite quickly because Alex has said a lot about it, and I also don't really have so many results. But the only point I want to make here is that the Koopman operator is adjoint to parent Frobenius, which we have heard before, and which means that we can also advance densities if we use it and it's adjoint, which also means that we can do things like uncertainty quantification for algorithms once we have an approximation of the Koopman operator, right? So if let's say this is our algorithm and it has some parameters, and then we want to study how these parameters influence the output of the algorithm, then we can use this technique as well because it's so closely tied to the stochastic interpretation of systems and the propagation of densities on the state space. And just to give you an example, this could be a hyperparameter of an optimization algorithm for a neural network, right? So these xn's are the weights of the neural network, and the p is, let's say, the learning rate of the algorithm. And now we can see how we can even do a distribution over the learning rate and see how these affect the overall dynamics independent of where we actually start training. I can skip this because you've seen it before, like how they are defined. Yes, this is something we haven't really talked about. High dimensional problems, right? And here, don't think about PDE. I'm kind of afraid of the theory, more afraid apparently than Alex, but think about many ODEs, right? Like maybe 100 different ODEs like here, and they all evolve over time. And now, of course, the challenge is that the algorithm acts on many variables, right? So the algorithm for an optimization problem might act on 100 variables, or a dynamical system might be written in terms of 100 ODEs. And our remedy, at least in this paper, is always we just hope that the algorithm itself moves down the states quickly to some lower dimensional submanifold of the ambient space, which happens a lot actually in multi-scale algorithms and also in algorithms that treat objectives with very different weightings, right? Which happens a lot in neural networks as well. So you have a loss function that is composed of different parts, and some parts have to be much stronger than other parts, and then you immediately have algorithms, or the optimization algorithms would immediately go down to a lower dimensional submanifold, at least because of this structure. And what we can do if there is a low dimensional submanifold is, for example, just use a dictionary that is adapted to these manifolds, which immediately works with the radial basis functions because they just depend on the distance locally between points, right? They don't really care about the ambient space dimension. And what we did, just as an illustration, is we defined a potential on a 2D manifold. We embedded this manifold in a 100-dimensional space. We said that the other 98 dimensions are very attracting, so it essentially moves down to this plane very quickly and then evolves kind of slowly towards the minima of this potential. And even though the space is very high dimensional and we would not have any chance to really sample the data well in this high dimensional space, or let's say define a Fourier basis for the operator in the 100-dimensional space, right? That's impossible numerically. We can still do a very good job in approximating the dynamics because we only start approximating it very close to this low dimensional manifold, and then the sampling of the points that we have to do in the high dimensional space essentially only needs as many points as we would need to approximate them on the 2-dimensional space. And this is just an illustration that in 1, 2, and 20, in the first, the second, and the 20th coordinate, the approximations of the trajectories are pretty, I mean, very good. And you can see that we only sampled 1,000 points, just normally distributed around 0, and then let them evolve towards this manifold. And of course, 1,000 points are never at all enough to sample a 100-dimensional space, right? It's crazy. But of course, sampling 1,000 points on a 2-dimensional space is enough, and that's why it worked. So some remarks on generators. You've seen the general idea that there is a Koopman operator semi-group for continuous system, at least, generated by the vector field, so that the group is just the exponential of the vector field. So we, in theory, at least formally, we can take the logarithm of this of a specific element of the group divided by delta t and get the vector field back. And of course, if you take a look at this, you can see that the eigenfunctions of this vector field and the operator are the same, only the eigenvalues are different by the exponential function, which means that to study the vector field, we can also study the discrete operator, right? That doesn't map infinitesimally, but that maps for a certain, maybe large delta t. But maybe one more point on this. What we can do in terms of algorithms now is that we can take a discrete time algorithm and just try to approximate a vector field that then would also give the same values as the algorithm would, right? And obviously this is not possible for all algorithms, because discrete systems do not always have a continuous analog, even though the converse is of course true, right? Because for a continuous or differential equation based system, you can always create the flow and then have a discrete version of it, but the other way is not always possible. But certainly for systems like this, like the Nesterov method, we can do it, and we can also use the Koopman operator to even get an approximation, a numerical approximation of this vector field that corresponds to the discrete version of the method, and compare it with the theoretical results. In this case, that were available, I think, only in 2014. Yeah, for Nesterov method, Candes and co-workers showed that there is a continuous version, and we can also get it with the Koopman operator now. Yes, and so the last point that I want to make is that we can also study chaotic behavior. And here I think it needs a few words of warning, because usually chaotic systems, of course, are not amenable to this standard DMD or EDMD methods, even though, of course, we can just apply it if we have data. But we have to think really, really carefully what it really means that there are suddenly some eigenvalues coming out of the EDMD algorithm, even though in theory, some chaotic systems don't have a pure point spectrum, except for maybe eigenvalues at 1 for the constant functions, but nothing else. And suddenly with the EDMD algorithm, we get some eigenvalues, right? Like what does it even mean? But here in this context, I didn't want to go into this discussion, because I wanted to focus on numerical methods that are specifically tailored to extracting the continuous part of the spectrum. So now I will sort of switch to another method to approximate only the spectral density of the Koopman operator for systems that have a continuous spectrum. And my little example here is Newton's method applied to this simple function. And what this means, if I apply Newton's method to this function, is that I try to find roots, in this case on the complex plane. And obviously you can see that the only roots that this function has is plus and minus I. Right, so Newton's method in the complex domain looks like this. And if we apply it, then you can see that, let's focus on this picture here. If we apply it to just randomly sampled points in the complex plane, then after some iterations, it certainly converges most of them to plus and minus I. And if you look at functions, like how functions on this space evolve, then you can also see, okay, after some time, pretty much everything is constant, and only the imaginary part flips between these two plus and minus I regions. But crucially, there's something going on the real line, right? You can see that there's some weirdness going on the real line. And this I think I don't really need to discuss, but I want to focus more on that. If we now pick a point here, an initial point for Newton's method on the real line, so on just here with exactly zero imaginary part, then this is a chaotic algorithm, right? It will not converge. It will never go back to some of the earlier points. And this is the sequence of points for 100 iterations, which was a little surprising to me because I didn't know. I just saw that this would happen. Funny enough, I can even compute explicitly the value of these points with Mathematica, because this is such a simple algorithm and such a simple function that we can get an explicit sequence of points that then is a chaotic sequence, which I really wanted to get in this case as well, because I wanted to get rid of numerical artifacts later for the approximation of the Koopman operator, just because this is chaotic, right? So I wanted to be absolutely sure that I compute the true points over a large number of iterations to then approximate the spectrum with these true chaotic points. I didn't want any numerical inaccuracies creeping up in here. And nicely enough, if we use the method from Korda and Methods, and Putinor as well, then we can even approximate the continuous spectrum of the Koopman operator for this method applied to points on the real line, right? And what this means here is that all eigenvalues lie on the circle, which makes complete sense because it is a chaotic system that never converges or expands. So you don't have eigenvalues anywhere else but the unit circle. And you also have only one pure point eigenvalue at exactly real part 1, imaginary part 0, which corresponds to the constant eigenfunction, which always is there. But all the other eigenvalues only have sort of a spectral density associated to them. And what we also have to choose here is the specific observable to get this spectral density. But maybe you can read the paper and understand more the actual algorithm they did. What is more important here, I guess, is that I used the exact points from the exact sequence that I showed you earlier and applied the algorithm to get this spectral density. And then I also iterated this algorithm by using a 10 to the minus 16 numerical accuracy, computed a sequence of points, computed the algorithm, or applied the algorithm and computed the result. And you can see that the results are very similar, which I guess, at least in this example, makes me hopeful that even though we only have very inaccurate data from chaotic systems, we can still use these methods to extract information about even the continuous part of the spectrum. This always, this is a good slide to summarize, I guess, about the potential and impact of this idea of using the Koopman operator to study algorithms. Obviously, it is a mathematical framework for algorithm analysis, and we can use it for explainability if you want. It is an efficient surrogate model for black box algorithms, even though also a word of warning that we, of course, have to sample some data. We have to have some data of these black box algorithms before we can build this efficient surrogate model. So there's always a trade-off. But we have shown in other papers that sometimes it's enough to sample a little bit to get a first early approximation of the surrogate, which you can already use to outperform or to very accurately capture the behavior of this algorithm and then outperform it in terms of efficiency, of course. we can gain insights into discrete algorithms by computing the continuous versions, which I think is more of a theoretical thing of interest, but maybe some person who does applications also has some idea here. We can do qualitative comparisons, which I think is very, very difficult to do if you think about black box surrogate models, right? Like how would you have a qualitative comparison of two algorithms if you just compute two surrogate models for them, and you cannot really get any information about the internals of your new black box surrogate models. But with the Koopman operator in particular, we can look at its eigenvalues, for example, and say that, just as a random example, if you compute it for stochastic gradient descent, compute the eigenvalues and see that they all lie inside the unit circle, and then we do the same for the Adam optimizer and see that some lie outside the unit circle, then there may be some qualitative difference between these algorithms. In this case, of course, related to their convergent behavior, right? And even more, I guess, general, we can also quantify inductive biases. So not just study how they converge, but we can also study the inductive bias of algorithms in terms of what they implicitly assume about the problem, and then do also implicitly, even though we just run them normally, right? So we don't study these algorithms individually to gather insights about what they implicitly have as assumptions, especially if you apply them to real data. But what you can do is apply them to real data, but then approximate the Koopman operator to get sort of this global mathematical framework where we can then actually compare them and study their behavior. That's it already from my side. If you want to read the paper, yeah, please go here. And if you have any questions after the discussion, then please shoot me an email.
All right, thank you very much. Thank you. Any questions?
Too much Koopman operator.
Hi, I have a question. So thank you very much for the talk. So I was just thinking, how do you attempt to choose a nice basis function according to algorithms? Like which algorithm has? So I think your paper uses this plate, like set with the center, which I don't really understand too much, but I'm just curious, like how do you choose what basis is the best? So, yeah.
Yeah, so as Alex has said, this is the most important question because we have to approximate it, right? We cannot really get the true Koopman operator, we have to approximate it. And so choosing a basis is the most important question if you want to have an approximation. And in my case, as I've shown you before, for high dimensional problems, it certainly makes sense to do either manifold learning in some sense and reduce the dimension before, and then use a standard basis like monomials or Fourier basis, or you can also just use basis functions that are adapted to your data, right? When in one example is these radial basis functions, so just pick a point and then use a Gaussian around the point as one of the functions. And then, of course, choose another point for another function and so on. This makes it independent of the ambient space, but it really, really depends on the application. And even more in depth, it also depends on the dynamic of your system, right? Because ultimately, what you want in an application is to approximate your observables of interest using those dictionaries, but you also in this context want to approximate eigenfunctions of the operator on your data using a linear combination of your dictionary if you use these linear methods. And this essentially means you have to pick a good basis for your function space. And if you do PDE, like normal numerical analysis or numerical computations for PDE, you of course know that picking a space of functions is even more crucial there, because if your observable, if your basis functions are not twice differentiable, for example, but your PDE solution has to be, then there's no way you can approximate it and have convergence as well. So you need to take into account specifically your application. So do you know something about what types of eigenfunctions you expect? And you also need to take into account in what dimension you actually want, or in what dimension your states are, right? In the case of this 100-dimensional example, it would not make sense at all to use a Fourier basis in 100 dimensions, because you just cannot enumerate all these functions.
Yeah, thank you very much. Yeah, that makes sense. So it depends on what system, and yeah.
Yes.
Thank you very much.
Sure. There's another question.
Yes, yeah, Enrique, yeah, you want?
Yeah, thank you, Median. Thank you, Felix. Great talk. So you see, again, as a PD person, I have some difficulties to figure out what eigenfunctions can be, right? Because you see, when you write the transport equation, right, and then you say eigenfunction, well, according to the transport equation, the profile of the eigenfunction has to be transported along the solutions of the ODE, right? On the other hand, this is a linear model, so eigenfunction means that the solution will be in separated variables, something like exponential lambda t times the eigenfunction. So in some sense, then you get something like a standing wave, right? So maybe dissipated, maybe growing, maybe oscillatory, but somehow there is a confinement, a local confinement of mass, which is against precisely the intuition that particles are moving according to characteristics. So how do you expect an eigenfunction to emerge out of these two apparently contradictory scenarios?
I think this was also the issue before when you asked it the first time. So this is not the Koopman operator, is the dual formulation of the Perrin-Frobenius formulation, right? And I think the issue here is that you think about the transport of densities using the Perrin-Frobenius operator, not this dual formulation with the Koopman operator, because the Perrin-Frobenius operator actually transports densities across the state space, and there certain like conglomerations of particles move really. But here also, as you just said, the only thing that happens is that functions get either oscillate or decay or explode. But this is all that happens, at least in the function space. And then this movement that you just described, according to the transport equation that would emerge from the agglomeration of the ODE particles, this movement only happens because you describe the coordinates. Let's say here in this example, the coordinates x and y, you express them as linear combinations of all these eigenfunctions. And then only sort of the overall sum will then describe this movement. I'm not sure if I explained it well, but you sort of have to think about the sum of all of these to then see the movement.
So the Koopman operator is not f of x dot nabla, not dot gradient?
Well, no, this is the infinitesimal generator.
Well, okay, so yes, the infinitesimal generator, yeah. Right? So then yes, the corresponding dynamics would be something like yt plus fx gradient y equals 0, right?
Yes, I guess. Yes.
Yeah.
That's still the differential version.
Yeah, and this is the transport equation for which solutions are constant along characteristics.
Yes.
Which are the solutions of the ordinary differential equation x prime of t equal fx of t, right?
Right, and I think you can. I don't have the. Oh yeah, I have the equation here. You can see that this is true, right? The values here are the same, transported just along right, over time. Yes.
Right. And then can you tell me again how if you give me an eigenfunction of k, right? So you are talking about eigenfunctions of K, right?
Yes.
So how this expression to the right, G phi x, will be equal to lambda Gx?
Yes, then in this case, obviously G would be an eigenfunction. But of course, not all of these observables are eigenfunctions. I'm not sure what you're asking here. Like,
so can you give me an example where such an object will really have an eigenfunction? I mean, not an invariant, because I mean there is a lambda, but it's basically the equation to be solved is G phi x equal lambda Gx, right?
I mean, one example is here, right? With this, oh, where's it? Here, yes. So here the monomials are eigenfunctions, even though, of course, the dynamics is just converging, right? This is Euler's method, and the system is a linear method. So a linear system, so it just converges to zero. But these are eigenfunctions that, well, have this property that we just talked about, and these are the eigen.
And what is the vector field f of x in that case?
Minus ax.
Okay.
So
yeah, but this is, yeah, but then f is f is a constant linear function, right? Do you know any nonlinear f of x that will for which you will be able to find eigenfunctions?
Yes, I think. Can I write a paper in the chat where we
or we can also discuss any other time, Felix. I don't want to take too much of your time or the other, so I can send you an email and maybe we can discuss one day in Zoom calmly, right, with the iPad and write down the equations. Okay.
Absolutely. Yeah.
Okay. Thank you, Felix. I send you an email then.
Okay. Yeah. Great.
Thank you. Ciao.
Yeah. So maybe you can post the paper for everyone on the chat. Yeah.
Of course. Yes. I will search for it.
So Alexandre, did you have a question? Or?
Yes, I just wanted to comment a bit, and then I had a small question. So I think eigenfunction, you can also look at their level set, and then it really gave us some indications. So for instance, in the case of limit cycle, there was a picture in the last slide by Felix. Then in the case of limit cycle, it's related to isochrones. So the level sets will be sets that will be mapped to each other after a period of time. And so it really gives information about the dynamics. Just wanted to add this. And so just a small question. It was about the fact that at some point, Felix, you said that for some algorithm, there is no continuous time equivalent, but I was not sure, but maybe I was too tired and I missed something. But why did you want a continuous time analog?
Well, no, I mean, I'm not saying we want this for our algorithms. I was just pointing out that for some we can get it, but for some other ones we cannot.
But otherwise we don't care because we just apply it in the discrete time framework, and this is fine, right?
Yes, but then, I mean, then other questions emerge, right? Like if we have an algorithm that does not have a continuous version, like a continuous vector field, and we approximate its Koopman operator, then this operator is not element of a semi-group anymore, right? Because we don't have convergence of the operators to some vector field. And then your method also might have some issues, right? Like if you want to then extract the generator for the group.
Yes, of course. So for instance, in my method is because I want to find the vector field, but so I assume that there is a vector field.
Right.
But if we are interested in spectral properties, we do not care, I would say.
Sure.
Or if I missed something, maybe I missed something. I don't know.
But I mean, it depends on what you mean by not caring, right? Like I would certainly be a little bit careful when I have an algorithm and I can adjust its step size. Let's say Newton's method, but bounded with some step size. But I know that there's no continuous analog, right? And then, like, what does it mean to make the step size smaller and smaller and smaller?
Ah, okay,
right?
yes, I see what you mean now. Okay, it's in this limit of the sampling time tending to 0. Okay, then I see.
Oh, great. Yeah, I see that Eric already gave a
Yes,
talk.
yes, I was just because I think someone asked this question about how to find good dictionaries. I just remember that Eric Borg gave a talk here and the same seminar series about 2 months ago, I think. Yeah. Yeah. All right. Any other questions? Yeah. Okay. I mean, I think yeah. Thanks again, Alexandre and Felix, for the nice lectures. So I'm going to applaud you on behalf of everyone. Right? Thank you very much. And
yeah, thank you for the invitation.
yeah, thank you.
Thank you.
Great questions.
Thank you. Bye bye. Thanks. Take care, everyone. Thanks. Bye.
Bye-bye.
Bye.
Goodbye.